We're going to step over Serde today. And I think the strategy that I had is slightly changed. I'm still probably going to quickly step over or go over Steepall and Candle, which are the the next libraries that I have here locally. I have a demo example to step over. And then probably what I'm going to do is build another website from scratch, which I already started with GPT. And I don't want to build on the other one that I already have because that's fully on Rust, and it was just like something that I've done really fast to have something to train with, train quizzes. But this one is probably gonna be more complex, and I'm probably at some point gonna use Monaco, which is VS Code's code editor. So I think what I'm gonna do is basically use React for the front end, and then Rust as a server. That's kind of the idea. But probably I'm going to work on that next time that I stream. So maybe I'll work a little bit on it offline as well. But the idea is going to be the same, just to create exercises or different types of exercises that help me minimize the friction between the intention or the ideas that I have in the architecture and the actual execution of writing the code and knowing like how to build everything. I already started the debugger here. Oh, something else that I realized from last time that I wasn't sure. Maybe I'll show that after I go over Serde here. But about Rail is that I wasn't sure about generic type, why it was going to a specific definition. But the reason why it was because it is defining that definition on the next line. Maybe I'll show there on the function that I clarify with GPT offstream. So here, so far it seems pretty easy to understand. IO is probably a built-in library that I think it has there explicitly. Great IO. I'm pretty sure I've seen this library as well. As the name says, is input output library. This is the standard library, so whatever. So this is gonna be a write of probably the input, I think. Something that, or maybe allows you to write to the output. Writes a buffer into this writer. How many bytes were written? Maybe we'll go over the execution, then I'll come back. Writer. I have to initialize this with passing a writer as arguments, and then it's gonna use this with formatter. This is the formatter here. Whatever. I can't. Maybe I can. So choose string. Just passing this struct, and he wants to serialize through a string. That's what it should be doing. First it does this to vac, then unsafe string from UTF-8. Check. And uses this macro here as well. And this one at least has the definition. It's gonna match the expression and then returns the value. So I think it's just a try catch block kind of thing, just to verify that the conversion was safe. So here you pass, so T, the generic type is the type of the value, which in this case would be point. Calling to string with points is gonna be this generic type. Is this generic type here? Pass this here. Is a vector, novel vector. So in this case, the writer is a vector, and the value is a point struct. That's what I want to clarify here before going on. So use the vector to build the serializer, to initialize the serializer, and then it calls serialize. This one is kind of weird to me. No, but I guess it's because of this type constraint here. So whatever type you pass here, it needs to be this. It needs to implement the same stuff that the serialize implements. And that's how it's possible to call here, I'm assuming. Yeah, so the trait, the serialize is a trait, and then that means you have to define. So I think that's, yeah, but I'm not really, like, maybe there is a macro. Yeah, so there is a macro here. So obviously I assume what's happening is that when you declare when you put this serialize and deserialize on top of here is gonna add the trait methods to this struct. So it allows you to call the serialize there from the point. And then here's the same thing that I kind of expected when I press F12 there. This is some compiler built-in stuff. So the compiler is gonna put the code, and I don't think that there's a. When I get to building the website, then I'm gonna think about these things. I wanna see like an effective way. I'm thinking about creating kind of like a funnel. Like knowing how this works under the hood is very obviously not relevant at all for actually building stuff. I would guess that most people that build things on Rust don't actually know what happens here, because it is kind of like a detail, let's say. So I consider important, obviously, to try to understand everything. But then obviously, if you're under time constraint, then you want to do useful stuff. So obviously, most of the time, you want to spend actually building and not diving into these rabbit holes. And that's the reason why I'm thinking about doing a funnel. So majority of the time, I should spend trying to do the things that are actually useful right now. So like learning the APIs or memorizing the APIs, becoming better at using the libraries and understanding like what can you use from which library, and becoming better at data structures and algorithms and these kinds of things. But then some percentage of the time I should also spend trying to figuring out like how does it work here. And also there's another thing about that I discussed with GPT, that some exercises are very slow. Like when you have to type the whole implementation is very slow and annoying. So I think this is a relationship between frequency. So the exercises that are slow to do, I do it at a lower frequency. And the ones that are fast, are easy to do, then I do it at a very high frequency. So probably on the website, I'm going to try to put like metrics or some mathematical equation under the hood that calculates the density of the exercise type. So I create different classifications of types, then create kind of a funnel where I can have like multiple exercise methods that are very fast, like the close cards of just typing the key parts of the implementation. Then I can do it like repeatedly at a very high frequency, which is going to help on retention. And then I have another thread that's very slow, but then it forces like reconstruction, because I think that one of the main things you need to learn effectively is active recall. This is the thing that allows you to build like the most memory. That's why building things is actually the most efficient, because you have to force yourself to actually come up with the answer yourself. And that's the thing that I'm lacking the most, because I have a tendency to, because obviously it's easier, like it's not effective if you want to build a lot of things to try to build it yourself, because like I said, you waste a lot of time typing useless stuff. So I have always have the tendency of looking for the path or least resistance, like using LLMs and agents, because then you build much faster and you're only concerned about the architecture and the overall view. But then obviously it creates this problem where it feels like you never have a good grasp of the actual execution. So when you can't use the like easy path, let's say, then you have to like, there's a lot of friction to look into the documentation or to talk to ChatGPT, because then it's gonna give you like a lot of irrelevant information for what you're actually trying to do. So the type of training I'm trying to do is much more things that I can do on a day-to-day basis that are actually gonna allow me to bridge that gap without wasting too much time. Like off-stream, then I keep using agents and other stuff to build very fast. On the long stream, I build like through routine. I build this more execution path, even though it's gonna be slower, I think. And this is weird. So I'm not really sure how it goes from here there. Because the saying is a string. This name here is a string. I don't know how does it call that? Here's the point. It's passing this. The writer is a vector. This is not a string, obviously, it's a serializer. So I don't understand how it goes, how it jumps from the macro to there. But I guess it's something from the compiler under the hood. Some of this stuff. Maybe this is inline here, or sure. It's gonna match this. And it's a raw token. It's not a number. Oh, is the default, so it's not a raw and not number. Then it calls this serialized. So I think that this is the string. This is similar to what I saw on the rayon as well. There was like, I think it was the macro as well. It was a similar thing, but the name was a different one because of another macro, I think. I guess this is just the name of the file. There's something happening with the macro that makes it, or that the file is important. The main file is important. So the thing that it went over here, then over here, I think. We're gonna return this compound map, I think. This stuff. In the south is this serializer. 5. So it's the value here. So I guess the first argument is always going to be the actual file. The key is always the file. And I think that it must have something to do with the macro. One of these macros, either this macro here or just the derived macro or something like this. Derived function. And the value is the value inside of this struct now. Realize field. Matter. These functions that decide what the object is going to look like are from the formatter, which was passed, I think, under the hood or inside of the library. It was passed here by default, I think. I think it was this one, maybe. I don't remember. Yeah, so it's passed by default here on the initialization. And maybe the value, maybe I'm reading this wrong. Maybe the data pointer is not the value. Or maybe it is the same here. I don't understand why it is a file. It now is the value. Yeah, so I think that this I here is the type. Was implementing serialize for this type. is the methods, serializer method. It calls the serializer method to this type that is going to be casted. Passes the type, I think. Or passes the value that is going to be casted. In this case, a float. So I assume that this writer is a vector, maybe. I think this self.writer is the vector. But I'm not really sure. Yeah, I think it is the vector. This may be underneath. There is another variable that is maybe another type that is maybe something else that I forgot, but that I've seen on the examples of the data structures, and I think it has something to do with the initializing memory without having to tell the type, because then it's something to do with the drop. So it can initialize without the memory being dropped, or something like this. Memory drop. So I'm gonna write this down because I kind of remember, but I don't remember why. Hmm. So here, based on the source there, I think it's pretty easy to understand what is going on. We're just gonna return as the other type. So it's basically converting based on this type here. It's converting to the self, I think. But the thing that I'm thinking about is that I remember from C++, from one course, I think it's Open Security Training, the name on YouTube or something like this, where there is a hack on C++ that is called type confusion, and it's because of the inheritance. And I think it has to do with typecasting as well, where the language think something is of one type but is from another. And the example I think I remember is whenever you have a derived class, then you pass that class as a pointer to a function as the base type, and then you return as other, like another derived type. So because you collapse into the base type from the derived, and then you cast it to another derived type, you can have undefined behavior on memory because you can have other stuff like other logic on the other derived type. But I don't remember really well if that's the situation. I think it has to do with dynamic casting as well, where this stuff can happen. So the main thing that I'm thinking about here is exactly that. Like, what are the consequences of these types of casting here? I'm gonna press F10 to go faster, try to get to the end. Probably spend more time studying this library specifically at some other points because I know this one is used a lot. So I wanna understand more. I kind of get it here briefly. Like from looking at this briefly, I kind of get it how it works, or like how they thought about this. But I'm very uncertain about. I'm very uncertain about the nuances of the how does it work. Like the type conversion that I talked about there, for example. It seems very simple, and I still like find it hard to think about generic types, but I'm kind of getting more used to it. I think probably over time, like studying more and more is gonna become easier and easier to think about. But I think that writer is a good example of this, where in this case it's passing a vector, but if I remember correctly, it is a generic type. And the way the library can do this is that it doesn't need to know anything about the type we're gonna pass, as long as it puts a constraint about the type. So all you have to do when you're creating a generic is think about like what kind of behavior I need the thing to do, and then based on that you look into something or create something that actually does the behavior, and then you don't need to think about like all the potential scenarios of the things you're gonna pass to the API because you already know like the limitation. Like the type needs at least to implement these kinds of things. But then like for things that don't have constraints is still very hard. But I think that it is a direct relationship. Like when you have a generic and you don't have constraints on that generic of what types it should be or what should what it should implement at least to be able to be passed as an argument for the function, for example. Like here, you don't, like on this case, you all you have to know is that the whatever type you're gonna pass here, it needs to implement this types here. So this is a union, so it's like on a Venn diagram when you have two circles, and like both of them are gonna be full. It could be either one of them. It has to be on the space that is inside of either one of them. So as long as the type you're passing satisfies this constraint, that means you can call any functions that these two things have. So you don't need to know. But in the case where you don't have the constraint, then it becomes a lot harder to think about, because then the type could, in theory, be anything you want to pass. But what this does then is that it significantly limits what you can do with the type, I think. Like what kinds of things you can pass, or what kinds of functions you can call from that type. We're not really sure. And maybe this is a good question to ask. Like if I have, what constraints does generic type introduce if I don't use the where clause? The creator vector of bytes, pretty much. And I assume that the bytes are obviously the UTF-8 of the bytes are supposed to be the equivalent of the UTF-8 for the type itself, or the syntax of the type, or the points, or maybe just the values and the name of the struct. Obviously, it wasn't enough time to really understand everything. I'll probably come back to this a lot of times in the future. So I didn't serialize the actual point type, just serialize the value to make sense. So I think that one of the things is that if you try to pass something that the JSON doesn't understand, then it's gonna throw an error, probably. You need to pass objects or like whatever. The constraints of the JSON grammar are gonna determine what kind of things you can pass as a value here. So I'm gonna, well, Let's see if I can get to the function that I was talking about. There's a function that last time. The problem is that there's too many things here. The, is a type that calls another, is a generic type that calls a function, and I was wondering, like, how does the compiler know where to go to the definition, given that I wasn't seeing anything that it would indicate that the definition that that, that would indicate that the definition it was going to was the correct one. I don't think the where is a union. A plus B means it has to implement both A and B. As soon as say both in front of a type makes that type optional, I think. Yeah, I'm not 100% sure about the details. The way that I'm reading the plus is like a union. So you have two circles, and then it could be either one of the spaces. It doesn't mean that the circles have to intersect necessarily. It's just that it could be either, it has to be inside of the region of the union. But you might be right that the question mark makes the one of the types optional. Remember that the question mark is used to catch errors, but I don't understand how it works, like fundamentally. I should write this now. It's the inner join. But if it does make it optional, I don't understand why they would do this. Because then like hmm, why even specify the type there then? Because if it is a union, then it shouldn't matter if something implements only the type that doesn't have the question mark. Like maybe you're saying that the constraint is that whenever you have whenever you have the plus, the type has to implement both of the behavior of both types. But then when you have the question mark, you're saying that it can be a type that only implements the serialized behavior, but it doesn't implement the sized behavior. That would make sense, I think. Size means it's optional for it to implement sized, which means size is normal compile type. Yeah, I think that could make sense. I'm just not 100% sure if that's how it works or not. Maybe don't remember if it was F or something. But it's gonna be too hard for me to find the base that I was talking about last time that I was confused about. I think it was something to do with F and then output. And maybe it was on this file. Yeah, I don't think it was here. Yeah, I don't think I'm gonna be able to find. I think it was something related to item. Was item and then had outputs as well. And when I pressed F12, it went to a specific definition, and I wasn't sure, but it was because it was defining the other generic type on the next line, and I don't remember the exact spot. I think I'm just gonna ask or send this to GPT to see what it says. I'm gonna read the response and then I'm gonna stop streaming probably. I'm gonna open a new thing. Oh, no worry, no worries. Yeah, I have no idea. True. I think you're right. The size is about knowing the size of compile time. I do remember something kind of like that. I had an error at some point related to this, but I don't remember exactly what it was. But I have no idea about the check mark. I know the check mark is used to catch errors, and it is slightly different than the result type. And I remember that some people recommend not using the question mark on some situations, but I don't remember really well like why. I think it was this. No, but it probably wasn't this because I think it was a related to a function. But here is very obvious that it's going to this type. But it was the same pattern that I was confused about. Like I didn't know how it knew where to go. But it's just because it was like specifying which type it is, either on the next line or on the previous line. Or maybe it was this thing here. The results. Or I think, yeah, I don't remember. So I'm just gonna stop this now. Because I'm not gonna find the specific thing. So I'm just gonna do a GPT sass, and then I'm gonna stop streaming.
The first important distinction is that from/into is not a memory cast. Rust has several operations that can look like convert type A into type B, but they mean very different things at the memory level. One may be on int t is actually for there is no maybe on int in the implementation you pasted, so it isn't involved in that conversion. But it's closely related to how Rust thinks about valid values in memory. Normally, if Rust says you have a, Rust lets t and x exists as a usable t, Rust is allowed to assume that the bytes backing x form a valid t. For example, Rust bool is not conceptually one byte containing anything. A valid bool must represent either false or true. Likewise, Rust t must be a valid reference. It cannot be null, dangling, misaligned, etc. And Rust string has internal invariants that must hold. So this is illegal. Rust lets bool unsafe stdmem uninitialized. The problem isn't merely you might read garbage later. The problem is that creating an invalid bool itself violates Rust validity rules. The compiler can optimize based on the assumption that a bool is always valid. Maybe on int t says something very different. Rust lets maybe on int t it means here is storage capable of containing a t, but I am explicitly not claiming that a valid t currently exists there. So Rust lets maybe on int u64 maybe on int is perfectly valid. Memory exists, but Rust does not treat those bytes as a u64 yet. Then you can initialize it. Rust let maybe on int u64 on int x dot write 123 now bytes encoding 123 and eventually Rust let value u64. Unsafe x dot assume underscore int the unsafe operation is basically you telling the compiler I guarantee these bytes now contain a value u64. Why is this useful? Mostly when you want storage before a value has been constructed. For example, Rust let me array maybe on int foo100 you can initialize elements one at a time. Foo. Initialize so far without lying to Rust and pretending all 100 foo s already exist. This is useful for implementing vector arrays initialize element by element custom allocators / containers FFI functions that write into an output pointer placement style construction low level data structure so that conceptual purposes maybe on int t separates memory capable of containing t from a valid t currently exists. That's an extremely important distinction in Rust. 2 from t / into u does not reinterpret memory. Now look at this. Rust simple t u into u for where u from t into self u from self you might initially read this as t bytes downward arrow. Reinterpret downward arrow u bytes, but that is not what it means. It means t value downward arrow run arbitrary Rust code downward arrow u value from this just a trait. Rust trait from t from value t self and implementation can do basically whatever it wants. For example, conceptually, Rust simple from foo from foo bar x foo. A 7 y expensive underscore computation foo.b. There is absolutely no requirement that size underscore of foo size underscore of bar that their layouts resemble each other. You might have foo 24 bytes becoming bar 128 bytes t allocation or the opposite. 3 so what happens to memory during into consider Rust leta t let u done semantically a move into self t u from self arbitrary conversion. Code b you notice that Rust into self takes self by value. That means ownership of the t is transferred into. Then Rust u from self transfers ownership into from. Eventually the conversion produces a completely value. Afterward the original t has been consumed. For example, Rust lets string let some type x dot into you generally cannot do. Rust printled x afterward because x was moved. For the compiler doesn't assume anything about their memory relationship. Suppose Rust can convert t u x t where u from t u from x to the type system level. The compiler knows only t exists u implements from t. It does not know from that bound that size of u alignment t alignment u layout t resembles layout u bits can be reused. Conversion is cheap. Conversion allocates conversion preserves numerical value. None of those follow from. It's simply a behavioral contract. From t for u exists downward arrow there is an operation downward arrow t rightward arrow u5. This is very different from transmute compare Rust u from x with something like Rust stdmem transmute t u x t's are completely different ideas. From value t execute conversion algorithm value transmute is much closer to bytes interpreted as t same bits bytes interpreted as u and therefore has extremely strict memory validity requirements. Then there are conversions. Rust lets u8 200 let u32 base 32 again. That is not transmute. Rust applies defined numeric conversion semantics. So it's useful to mentally separate from behavioral conversions language define primitive conversions pointer cast change pointer interpretation. Transmute reinterpret representation maybe on int storage that does not yet claim to contain valid t. These concepts are related to types, but they operate at very different abstraction levels. 6 your generic question gets to something fundamental. Consider Rust foo tx t what can I do here? The key idea is that the function must make sense for every possible t satisfying its bounds. And you gave no explicit trait bounds. Therefore you know almost nothing about t. It could be Rust u32 string my struct hash map x y socket atomic u64 some massive thing etc. Therefore this is impossible. Rust foo tx t printled x because that requires Rust t display likewise. Rust x clone requires appropriate clone support. This Rust x requires an addition operation. This Rust x serialize requires serialize. This Rust x some underscore method only works if the compiler knows such a method exists through inherent / type knowledge or trait. Bounds. Without constraints, t is basically an opaque type. 7 but there is actually one hidden / default constraint. This Rust foo tx t doesn't quite mean t literally any Rust type because Rust implicitly inserts Rust t size so it's approximately Rust foo tx t where t sized. Size means the size of value of this type is known at compile time. Examples: Rust u32 size string size vec u8 size my struct usually size but Rust stru u8 some trait are dynamically sized types. Their size cannot be encoded solely by the type itself. 8 this explains here. Size your actual code says Rust serialize underscore t myself key t result where t size serialize does not mean the size constraint is optional. At least not in the everyday optional value sense. It means remove the normal implicit requirement that t sized. So Rust t size means roughly t may be sized or t may be dynamically sized. This is why it looks unusual. Normally Rust t implicitly means Rust t size adding Rust t size relaxes that implicit constraint. Think t size must be statically known t. Size do not require statically known size. It doesn't mean maybe add the trait. It's more like size is not required. 9. Why can t work when t sized? Because even though dynamically sized t cannot normally exist directly as a local value, Rust lets str doesn't work. It can exist behind a pointer / reference. Rust lets str the reference contains enough metadata to locate and describe the value. This becomes particularly interesting from a memory perspective. For Rust u64 you effectively need address something conceptually like 0x abcdef 00 because u64 is always 8 bytes. The compiler already knows address 0x abcdef 00 length 8 bytes but consider Rust u8. Compiler cannot determine the slice length just from the type u8. So the reference contains metadata u8 data pointer 1 2 3 4 5 length. 5 similarly Rust str conceptually contains data pointer length and a trait object such as Rust 9 some trait typically behaves conceptually like data pointer readable ptr. These are often called wide pointers. So size absolutely can affect the possible representation of Rust t itself. 10 now let's remove your bounds original Rust serialize underscore t myself key t result where t size serialize. Suppose we change it to Rust serialize underscore t myself key t. Result 2 things change. First, t becomes implicitly sized, you lose Rust t size. So now t must have a compile time known size. You can directly instantiate the function with things like Rust t strt. U8 whereas Rust t size permits them. For example, given Rust let str hello the original function can conceptually instantiate Rust serialize underscore t strt because Rust str size is allowed. Without size, t str doesn't satisfy the implicit size requirement. 11 more importantly, you lose serialize. Look at this line. Rust key. Serialize map t serializer ser. Serialize the compiler allowing this because you promised Rust t serialize. The compiler knows whatever t turns out to be downward arrow there is a serialize implementation downward arrow. Therefore serialize can be called remove. Rust serialize and now the compiler sees Rust key t and asks how do I know t has a method called serialize? You haven't told it. So you get a compiler. 12 generic bound is essentially information supplied to the compiler. You can think of Rust foo tx t as giving the function almost no knowledge. T size known because implicit size basically nothing else. Add Rust t serialize and now t size serialize operations exist. Add Rust t clone debug partially q and the compiler now has t size clone debug partially q. Therefore you may write operations that rely on those capabilities. Generic bounds are not merely documentation. They directly define the operations legal inside the generic implementation. 13 an interesting way to think about generics. Imagine Rust mysterious tx t inside that function. T is deliberately hidden from you. Pretend someone hands you a black box. T they don't tell you what's inside. What can you safely do? You can say I have a reference to it. You can pass that reference somewhere else that accepts arbitrary t. You can get a raw pointer Rust list const tx. You can ask things that don't require type specific capabilities. But you cannot suddenly say add it printed serialize it clone it compare it sort it convert it. Because those operations don't exist for every possible Rust type. Then Rust t serialize is like someone adding a label to the box. T guarantee implement serialize. You still don't know what t actually is. But you know one thing it can do, and that's enough to compile Rust t serialize. 14 your exact bound has a nice interpretation. This Rust where t size serialize can be read almost literally as I don't care what concrete type t is. It doesn't even need to have statically known size. The only behavioral thing I require is that it knows how to serialize itself. That is why the implementation can remain completely ignorant of whether t is Rust string str u64 might be some other type because it doesn't manipulate the internal representation. Instead it delegates Rust t.serialize to the type serialize implementation. 15 there's another deep compiler distinction here for generic function Rust foo t serialize x tx.serialize. Rust first type checks the generic function itself using the guarantees from the bounds. It doesn't need to know that someday Rust t string or Rust t my struct to establish that the code is valid. It reasons given t implements serialize therefore serialize t is legal. Later during code generation Rust normally monomorphize generic code for concrete types. So conceptually you might have Rust foo string foo u64 foo my struct turning into specialized machine code. Very roughly generic source foo t monomorphization foo string foo u64 foo. My key at that stage the compiler knows the actual layout of each concrete t and can optimize aggressively. But the source level generic body is only allowed to rely on what its bounds guarantee. That's a really useful rule to keep in your head. 16 and this connects back to Rust's whole memory model. These mechanisms operate at different layers. Generic type t what do I know? Trait. Bound size value semantics ownership borrowing from TT behavior converting reference T right where arrow u value points to valid. T memory layout size alignment. Metadata size T. Size T thin T possibly wide T meanwhile maybe on T the distinction especially. Keep is a type is merely a number of bytes in Rust. A type tells the compiler how much storage is involved, how its aligned, which bit patterns slash values are valid, how ownership works, whether destruction is required. What references to it mean, what metadata pointer needs, what operations are legal, which invariants the optimizer may assume that's precisely why maybe on T exists. Sometimes you need the storage slash layout side of T. Without yet making the stronger claim that you possess a valid T. And that's also why MVU should not be thought of as changing the type of some bytes. It's consuming one valid type value, running a conversion operation, and producing another valid type value.
So obviously I can't really trust 100%, but I think it's most likely correct. It's kind of weird that it's said. So the first thing that is said is that the size is implicitly put on types. So all types have to be sized. So in size means that the type has to be known. The size has to be known at compile time. Then it said that it doesn't mean that this question mark has to be optional, but it says that it's not required. So in a way, it's kind of the same thing. But is it, maybe there is a difference there. But I understand what it's trying to say. It's saying that it's basically relaxing the constraint that Rust has by default, which is that the size has to be known at compile time for the type. And I think on this case makes sense. And then it's saying that it only has to implement the serialize, which I think is a trait there that has the serialize function. And another thing that I think is useful to think about is that it is just like I said, and I think makes sense. And for this, I don't need to rely on ChatGPT. I think that it's most likely correct that whenever you have a generic and you don't have the where clause, I think a good way to think about it is that it's just like a value, so or an object. So generic types by themselves make more sense if you want to implement a region of space. But then you can't really expect the region of space to have behavior. So it doesn't have the pathways. And whenever you see the where clause is when you need to specify how that space is going to be moved across time. That's how it works. Because the where is the thing that allows you to determine what kind of behavior the generic thing can do. So I think that for things like vectors, it makes sense to use a generic type without the where clause because you only need a box. And it's basically the same principle in Haskell that is kind of fancy that people talk about, which is the monad, which is the monoid on the category of endofunctors. It's basically a fancy way to say a container or a map. So whenever you have something that you just need to move from one place to the other, but you don't necessarily know what shape that thing is, you use a generic. But when you need to know both when you don't need to know what shape it is, but you need to know where you can pass that shape into, the pathway that the shape has to traverse, then you use the where clause. It's kind of like the where clause is the constraint of the space that you're trying to move the data. Implicitly, everything is sized. Yeah, according to GPT, that's the case, and I think it is probably correct because I do remember vaguely I had some issue like that where I hit an error because of the size, and it was something to do with this. So I think it's very likely that it is correct. So everything has to be sized by default, and in some cases, I think there may be an init that is said there as well. Is that in some cases you need to allocate memory, but you don't want to say the type that the memory is going to have. But it's kind of confusing because I don't know if the reason why is because of the drop behavior. Like if you, or maybe it's because like, yeah, I think that makes sense. So like in a situation where you have a class or you have a struct that you're going to use generics, you don't know what type the struct's going to be initialized with. So because of that, you're forced to use the maybe on init because you don't want to, like you don't have enough information to tell the compiler what kind of type you're going to have on that region of memory. So I think that makes sense. where is mostly easier to read. Yeah. I'm gonna stop here, and I think next time I'm just gonna probably go over the other two libraries, or I'm going to, which is SQL and Kendall, or I'm going to start working on the website for building quizzes, and basically I'm gonna aim to build a website that allows me to have like a, the ideal situation would be that I have the like a complete system, and I don't have, after the system is done, I don't have to think about anything anymore. I just do like a ritual every day where I spend 1 hour on the website training, and then the website automatically knows everything that I need to train to minimize friction between the way that the concepts I have on my mind and how to execute them in Rust. Yeah, so see you later, man.